Hello dear students, welcome back to Easy Notes. Today we'll be starting the part D, that is the last part of this chapter, critical angle and total internal reflection. Okay, let's see. Transmission of light from a denser medium to a rarer medium. Okay, when light travels from denser medium like glass or water to a rarer medium like air, it's partially reflected back into the denser medium and partly reflected into the rarer medium. It happens like that. Okay, the complete light won't be refracted, or the complete light won't be reflected. After some time it can be completely reflected, but usually happens that whenever the light is incident on the surface, after after reaching the surface, it will get refracted, right? From denser to rarer, it will get refracted away from the normal, but some portion of the light gets reflected. So as we keep on increasing the angle of incidence, the refracted ray becomes a bit weaker. Okay, so the refracted ray bends away from the normal. So actually what happens here? What is critical angle? What is total internal reflection? I'll explain you in a single page. After that we'll be just keep on reading. Okay, so let us consider this as a boundary. Okay, this is our denser medium and this is our rarer medium. Okay, now here there is an object. Okay, when the object is here and the ray falls on the surface, as this is what? This is the incident ray, right? And this will be our normal. This is normal. Now it will bend towards normal or away from normal. It's going from denser to rarer. It will bend away from the normal like this, right? This is the angle of incidence I1. This is the angle of refraction R1. And if I increase the angle like this, again this is our normal. This is the angle of incidence I2, and the refracted ray will bend more, right? In this way, this will be the angle of refraction R2. After some time, what happens? I'm increasing the angle more till here. Now this is our normal and this is our angle of incidence I3. Oh, what happens is the refracted ray grazes this boundary. Grazes this boundary like this. The refracted ray what does what? It grazes this boundary and refracted angle becomes 90 degree. Whenever the ray passes from denser medium to rarer medium and the refracted angle becomes 90 degree, then the incident angle will be known as critical angle C. Once more, whenever the ray passes from denser medium to rarer medium and the refracted ray makes an angle of 90 degree with the normal, then the angle made by incident ray will be known as critical angle. Okay, now what happens if the angle increases more than critical angle? If the angle increases more than the critical angle, now instead of refraction there will be reflection. Instead of refraction there will be reflection. This reflection is known as total internal reflection. This reflection will be known as total internal reflection. Okay, this process will be known as total internal reflection. What is total internal reflection? Whenever the ray makes an angle with normal greater than critical angle, then the ray gets reflected back into the same medium. That process is known as total internal reflection. If the refracted angle is 90, that is critical angle. The incident angle will be critical angle. If the angle of incidence becomes greater than critical angle, then the ray gets reflected back onto the same medium. This process is known as total internal reflection. Okay. Next. So we'll learn here one by one. Case 1. What was case 1? When the angle of incidence is smaller than critical angle. These two angles are smaller than critical angle, right? So what happens here? The ray partly reflected and mostly refracted into air. Okay. The angle of refraction R is greater than the angle of incidence. We are seeing here. R is greater than I. R is greater than I. Okay. As I increases, R also increases, but refracted ray becomes weaker. It starts becoming weak. At certain angle, R becomes 90 degree. The angle of incidence is called critical angle. When the refracted ray becomes 90 degree, when the angle of refraction becomes 90 degree, then the angle of incidence is said to be critical angle. So the refracted ray travels along the boundary surface and is very weak. It will become too weak. So while increasing the angle next time, the refracted ray is gone. Only the reflected ray remains. That process is known as total internal reflection. Let's see. When the angle of incidence is greater than critical angle, so no refraction occurs. The entire light ray is reflected back into the denser medium. This phenomena is called total internal reflection, and the boundary surface behaves like a mirror. This behaves like a mirror and it comes back to the same medium. Okay. Next, critical angle. We have learned critical angle is the angle of incidence in the denser medium corresponding to which the angle of refraction in the rarer medium is 90 degrees. Let us see the relation between critical angle and refractive index. So this was the boundary. This for an angle of incidence, and this will be our angle of, this will be refracted ray. This is refracted ray and this is incident ray. This is I is equal to C and R is equal to 90 degrees. Okay. Okay. Here let us assume mu1 refractive index. Here it is mu2. So we know Snell's law. According to Snell's law, sin I upon sin R is equal to mu2 upon mu1, right? So sin I upon sin R. What is sin I? Sin I is sin C upon I is nothing but C. Sin R is sin 90 degrees is equal to mu2 by mu1. Sin 90 is how much? 1. There is nothing but this is 1. Therefore, we can say that sin C is equal to mu2 upon mu1. So C will be equal to sin inverse mu2 upon mu1. Mu2 is the refractive index of second medium, mu1 is the refractive index of first medium. First medium is denser and second medium is rarer, or else we can write it as sin inverse mu r upon mu d, rarer medium upon denser medium. Okay. Next, factors affecting critical angle. The critical angle depends on the refractive index of two mediums. Since the refractive index depends on the color of light and temperature, the critical angle also depends on these two factors. Critical angle depends on two things: rarer medium refractive index and refractive index of denser medium. So as the refractive index depends on wavelength and temperature, critical angle also depends on these two things: dependency on color, that is nothing but wavelength. Refractive index is highest for violet and lowest for red. So therefore critical angle is smallest for violet and largest for red. It means that critical angle increases with increase in wavelength. Critical angle is directly proportional to wavelength. Next, dependency of temperature. When the temperature increases, the refractive index of the medium decreases. As the temperature increases, refractive index decreases. Therefore, critical angle increases with increase in temperature. So critical angle is also directly proportional to temperature. As the temperature increases, critical angle also increases. As the wavelength increases, the critical angle also increases. Okay. Next, total internal reflection. We have studied this. When a ray of light traveling in the denser medium is incident at the surface of a rarer medium at an angle of incidence greater than critical angle, for the pair of media, the ray is totally reflected back into the same medium, that is nothing but denser medium. This phenomena is called total internal reflection. This you need to remember what is the essential conditions for TIR, total internal reflection. The light must travel from denser medium to rarer medium. First condition, light should be traveling from denser to rarer medium, and the angle of incidence must be greater than the critical angle for the pair of media. These two conditions, if it satisfies, then total internal reflection can occur. If they don't satisfy, there is no total internal reflection. Okay, next, total internal reflection in a prism. Okay, PIR through 45 degree, 90 degree and 45 degree prism or a right angle isosceles prism like this, 90, 45 and 45 degree. So what are the types of total internal reflection we can see in this? Total reflecting prism, a prism having angle of 90 degrees between its two reflecting surface and the other two angles should be equal to 45 degrees is called an total reflecting prism, because the light incident normally on its surface on any of its face, here, here or here, suffers TIR inside the prism. Due to this behavior, a total reflecting prism is used for the following three purposes. What are those three purposes? The first purpose, to deviate a ray of light through 90 degrees. When the light enters a right angle prism normally, means it's entering like this. Wait, let's change the color. It's entering like this normally. So now what happens? It's entering normally. This is actual normal. What will be this angle? This is 90, right? This is 45, right? And this is also 45. So here this is 90, this is 45. This will also be 45, right? So I can say this also as 45 degrees. This is also 45 degrees. But the critical angle of prism is 42 degrees. Remember, the critical angle of glass prism will be 42 degrees. So it is greater than critical angle. Here I is greater than critical angle. So total internal reflection occurs. It will be total internally reflected. In reflection, what happens? Angle of incidence will be equal to angle of angle of incidence will be equal to angle of reflection. So like this will be reflected back like this, and this angle will also be 45 degree. So see here, to deviate a ray of light through 90 degree, actual ray of light was in this way. Here final ray of light is downward. So by how much angle it is deviated? It is deviated by an angle of 90 degrees. It is deviated by an angle of 90 degrees. The reflected ray then emerges normally from other face. It is emerging normally from this face. As a result of the light ray is deviated by 90 degree. It is used in periscopes. Remember, it will be used in periscopes. Now, the other use of this, to deviate a ray of light through 180 degree. Through 180 degree. Okay. Now, the ray goes from here like this. The ray goes from here like this. Like this. Okay, the ray is going like this. Now, how much will be this angle? This is how much? This is 90, right? This is 90. This is 45, and this will also be 45. Here this is 90, so this is 45. This will also be 45 degrees. Simple. So what happens? It gets total internally reflected like this. Now it got reflected by an angle of 45 degree. So again, this is normal now. Now again, this is 45, this is 90, so this will also again be 45 degrees. Again, it will get total internally reflected. Matlab 2 times there is a total internal reflection here. See here, like this, 45 degree. So by how much angle? It started like this, it's coming back like this. By 180 degree angle, the ray is deviated. The light ray enters the prism normally and undergoes 2 successive TIRs. Each reflection deviates by an angle of 90 degrees. See, 90, 90. So the total deviation becomes 180 degree. It is used in binoculars, cameras to invert images without a loss of brightness. without a single loss of brightness. It is used to invert the images. Okay. Next, to erect the inverted image without deviation. Erect the inverted image without deviation. Without deviation, how we can generate the inverted image? So let us see. There is an object like this. Okay. There are two rays coming out. 1 and 2. Okay. 1 and 2. So what happens again? This will get refracted inside because denser to rarer medium, right? Okay. Sorry, rarer to denser medium. It will get refracted inside like this. Okay. Now this angle will be greater than critical angle. If we calculate, it will be greater than critical angle. Okay. Now what happens? This will get reflected back by this way, like this. If you draw it clearly with scale and pencil, it will be parallel. Okay. See, the image was like this, but this image will be like this, inverted image, to get an inverted image. So the emergent ray are parallel to incident rays. They are parallel. The inverted object gives an erect image without deviation. Gives an erect image. If I take this image like this image will be like this. Simple. Object like this, used in slide projectors. Where it is used? In slide projectors. Just a minute on the AC. Okay, in slide projectors. Next, TIR in equilateral prism, 60, 60 and 60 degree. 60, 60, 60 in equilateral prism. 60 degrees, 60 degrees and 60 degrees. A light ray entering normally undergoes TIR at one phase. So it will enter like this normally. What happens now? It's entering normally. So this angle, this is 60, this is 60, this is 60. 60, 60, 60, right? So this will be 30 degrees. This will be how much? 30 degrees. Now, will it get deviated, internally reflected? It gets deviated by 60 degree and emerges normally. It gets deviated by 60 and emerges normal. It's entering normally, right? Sorry, my bad. It was entering normal. Just a minute. Array. Okay. See, it's entering normal to the one phase like this. Sorry, my bad. Like this. Normal to the one phase. Okay. This is 90. This is 60. This will be 30 degrees. Now this is normal. So how much will be this? This angle will become 60 degrees. Now, if it comes and hit at 60 degrees, 60 is greater than 42, it will get reflected back, right? How? It get reflected back like this, right? At an angle of 60 again. This will be 60. See? At an angle of 60 degree. Why? 60, this will be 30 and this will be 90. It should be 90, right? See, it gets deviated by 60 degree and emerges normally. It was going like this. See, this is 30 and this will also be 30. So it gets deviated by 60 degree. Total deviation is 60 and it emerges out normally. It will emerge out normally. A parallel beam may split into two equal beams at 120 degree. Two equal beams at how much angle? 60 plus 60, 120 degree. So it is used in optical instruments. Next, TIR in 30 degree, 90 degree and 60 degree prism. Let us assume this is 90, this is 30 and this is 60 degrees. Everywhere. 30, 60 and 90 degrees. Okay. A light ray entering normally undergoes TIR at one phase. Okay. Let us enter a light ray normally like this. This is 30. This is 90, so this will be 60. Right? This will be how much? 60. Again, same. Normally through one surface, right? Okay. Hey. This is wrong. This is, see, they have copied this thing there. So this is wrong. Listen to me. What happens here? This entering like this. No, what happens is this angle will be how much? See, this is 90. This will be 60, right? See, 90, 30, and 60. So this angle will be 30 degrees, right? Okay. Now 30 is less than 42. So will it get reflected or refracted? It will get refracted. So it will be refracted like this. Out. Simple. Now, what happens in this? If it comes like this way. It takes a refraction, right? Okay. This is normal. Occurs refraction. So it will go like this somewhere. No. This is 90. This is 60. This refract. See, this is perpendicular. Right? This is perpendicular. So what happens here will be, see, it's going like this. This is 30. Okay. It will go here. If this is less than 90, it will come outside, away from normal. Okay, like this. Now, here, if it comes like this, this is normal. This angle will be 60 degrees, right? Because this is 30, this will be 60. Now, it will get totally internally reflected like this, by an angle of 60 degrees. Again, what will be this angle? If this is 60, this will be how much? Wait, this will be 90, right? This is only 90. It will go like this only. See, this same thing as this. This won't be 90. Wait. Just a minute. Give me a minute. See here. This is normal. Okay. Now what happens is, this total is how much? 60, 60, 120. This will be 30. And this 30 plus 60, 90. 90 plus 60 is 150. So this will also be 30. 30 and 30. This will be 30, 30, 120. This total will be 120 degrees. So this is 90 degree. Okay, this is how much? 90. If this one is 90 degree, then it will get refracted, right? Because it's at an angle less than 90, that is nothing but 30 degree. So it will get refracted like this, outside, away from the normal. Done? Next, use of TIR. Instead of plane mirror, use of TIR prism instead of plane mirror. Let us see. A TIR prism is referred over a plane mirror because it reflects 100% of the light, no loss of intensity, image brightness will remain constant, and the plane mirror lose brightness over time due to absorption and silvering damage. But TIR prism does not lose any intensity. Okay. Next, it is used in periscope, binocular, and cameras. We have studied that. Next, difference between TIR and reflection from plane mirror. Just now we studied. That will be same. See, it takes place only when light passes from medium, from a denser medium to rarer medium at an angle greater than incident angle, a critical angle. Okay, but here it takes place when the light is incident on a plane mirror from any medium at any angle. Here the angle should be greater than critical. Here the angle can be any angle. Next, the entire light is reflected. The major part of light is reflected, while the rest is refracted and absorbed. Some is refracted, some is absorbed. Here entire light will be reflected. There is no loss of energy. There is a loss of energy. Here the energy will be same. Here the energy will always be less than the initial energy. The image is much brighter and the brightness remains unchanged. But here the image is less bright and the brightness gradually decreases. Okay. Next, some consequences of TIR. One will be mirage. On hot days, what happens? A wet road or a water-like appearance is seen due to total internal reflection. It is seen in like desert types. Okay, desert type places. We can see a wet road type thing, but there will be no wetness. It will be dry itself, but it will look like that due to TIR. Next, shining of an empty test tube in a water. If you put an empty test tube inside the water, the rays will get reflected by due to TIR only. Next, cracks in glass shine. You have seen, right? Why does a crack shines? Because of TIR itself. Next, sparkling of diamonds will also be due to TIR, and optical fiber transmit the signal from one part to another. That is also due to TIR. Okay. Next, first question. A ray of light is incident normally on one face of an equilateral prism. The ray gets totally reflected at the second refracting surface. The total deviation produced in the path of ray is, see, it is normally incident, right? This one, normally incident. By how much angle is it deviated? 30 plus 30, 60. 60 degrees. Okay. Next, a ray of light enters a rectangular glass slab submerged in water at an angle of incidence 55 degree. Okay. Does this ray undergo TIR when it moves from water to glass? From water to glass. Water is a rarer medium and glass is a denser medium. So no. Answer is no. It does not undergo TIR. Why? Because it's moving from rarer to denser. For TIR to happen, the ray should move from denser to rarer. Next, out of the three rays I, J and H shown in the diagram, which ray will suffer TIR while inside the prism? Okay. Copy the diagram to complete the path of ray which we have named in A till it comes out of the prism. Let's try all of them. See, it will come here in words like this. Wait, let me change the color. Like this. Okay. When it falls, this is 90, this is 60, this will be 30. Angle will be 30. This angle is 30, but this angle will be 60 degree, right? Because this is 30, so this will be 60. It is more than the critical angle. So it will get total internally reflected like this. 60, so it will make an angle of 60, right? 90, so here it's 60, 30. 30 plus 60 is 90. So here again it will be 90. This will also be 90. So it will come back like this. Like this. Total internally reflected. This angle will also be 60 degree. So J will be totally internally reflected. Why not I and H? Let's see them. Let's follow H. It goes like this from here to here. This is 60, right? Sorry, this is 60, this is 90, so this will be 30. If this is 30, so this will be 60. Now, this is the what? Normal. So this will be 30. It is incident at an angle of 30 degree. So this is not possible. How about I? Again, I falls here like this, right? So we'll make normal. As this is 30, this will be 60, and this will again be 30. So it will also getting incident on 30 degree angle. So it will also not suffer what to TIR. So only J is the right answer. J is correct. Done. Try it once by yourself. Next, small air bubbles rising up fish tank appear silvery when viewed from some particular angle is due to TIR, right? Silvery because of TIR. Next, assertion reason. Okay. See, TIR occurs when light travels from denser to rarer. True. This phenomena happens because the angle of incidence is greater than the critical angle. True. And it is also an explanation of. Acha, we have two. So first one is A. How about second one? The path of light is reversible in refraction. No, reversible is only in the path of light is reversible in refraction. Yeah, reversibility we have studied, right? In reflection, it's not reversible. Next, the angle of incidence and the angle of refraction are always equal. No. It's not always equal. So it will be option C. Okay. Next. Why do we use red color as a danger signal on the top of skyscraper? Why? Because of less wavelength. Because of less wavelength, it can scatter more. It can be easily, it will scatter less. Because of more wavelength, right? Red have more wavelength. Because of more wavelength, it will scatter less. So it can be seen from far away as well. Because it's not scattering. That's why we use a red color for signals. Next, the diagram below shows the path of blue ray through prism. Calculate the critical angle. Okay, let us calculate critical angle. So this is our normal. This angle will be 90. So this angle will be how much? Total is 133. So 133 minus 90. 133 minus 90 is 43. Critical angle is how much? 43 degree. C is equal to 43 degrees. For option sub question first, C is 43 degree. Next, what is the measure of angle of prism? This. Okay. See here. This is 90. This is 180 minus 33. 133, sorry. Total is 180 minus 133. 180 minus 133 will be how much? 133, 47. This will be how much? 47. So this will be 90 plus 47, 137. 180 minus 137 will be 43. How much? 43. Second is also 43. Angle of prism is also how much? 43 degrees. Next. Which color should replace the blue ray for the ray to undergo TIR? To undergo TIR, the wavelength should is the critical angle greater than this? If I add wave gear to undergo TIR, blue ray is undergoing critical angles here. It's grazing the path, right? The angle of incidence should be greater. To increase the angle of incidence, to increase the critical angle, we should increase what? We should increase the wavelength, right? So it's blue. We can use any of this by increasing the wavelength. Then next, the diagram shows a source P embedded in a rectangular glass block ABCD of critical angle 42 degree. This has a critical angle of 42. Complete the path of ray PQ till it emerges out of the block. Okay. This is the normal. If this is 42, or this angle will be 48, right? Next, the critical angle is 42, but incident angle is 48. So it will be total internal reflection like this. This will also be 48. Now here, this is 90, right? So what will be this angle? This angle will be, see, this is also 90, right? 90, 48, and this will be 42. This will again be 42 degrees. At 42 degree critical angle, so the path will be retraced like this. This will be the actual path. Okay. Next, the diagram below shows A, B, C, and D. Okay, show in the diagram the path of these rays. Okay, the critical angle is 48 degrees. Name the phenomena which B and D exhibit. Okay, let's draw the path of these rays. This will go straight in a straight line like this. Simple. This will be refracted like this. This is 48 degrees, so it will be grazing. 60 degrees, so it will reflect back. This will be the actual answers. Simple, easy. path will which phenomena B will undergo refraction and D will undergo TIR, total internal reflection. Okay. Next, the last question of this chapter and of this part. The diamonds glitter in dark because they emit light? No. They have very small critical angle due to very high refractivity. Yeah, exactly. For instance, no chemical reaction and all. No. Then, so by this we'll complete the chapter 4, part D, and this chapter is completed. We'll meet in the next chapter, that is refraction through lens. Till then, keep supporting and keep learning from Easy Notes. Bye bye.